Okay, so today I'm going to talk about the surface integration of vector fields. Um, I'm gonna in this video I'm gonna give you guys a intuition, like what does that thing actually means in real life and how do we really calculate with this surface integration of vector fields. On YouTube there are plenty of videos on this, and I watched fairly most of them, but the thing is I couldn't actually when in the first time I was watching those, and I wasn't able to correlate between the theoretical parts and how does this thing actually work in our physical world. So here's my trying to make you guys understand it better, probably. So as you can see here, I have written flux. So what I'm actually gonna start with is flux of vector fields, because the surface integration is actually the flux calculation of a vector field. And you guys can say, why do we need fluxes? So fluxes are basically needed in the physics, and some in broader levels there are many applications. Let's just start with the definition of flux of vector field. So here, let me pick up the color. So flux fields basically means how much of a vector field passes through a surface. So let's consider this a surface. You can see it is like a coin-shaped surface, a circular, and there we have some vector fields, let's say F. So these vector fields passes through these surfaces, and the amount of F passing here, let's say for visually calculation and just for saying that 3 lines are passing, so we can say that this is actually 3F, because you know the magnitude of F, we can say that this is F, so like 3F amount of lines are passing through. And if we increase the field lines like this now you can see this is pretty much dense, and so suppose now it's 5F passing through the surface, so the flux has severely increased in the next example. So here one thing you can see that the flux lines are calculated when the vector fields are crossing perpendicularly. By perpendicularly, what I actually mean is that if let's look closer thing, if we take the normal vector of this surface at any point, let's say this is our n cap, so it is our normal vector. So what we are actually taking is that the vector field that lies on, or the projection of the vector field upon the normal of the surface. So in another example, let's say we have our surface here is, but this time we have our vector fields going in this direction. Now, as we have seen earlier, the normal is perpendicular, always perpendicular. This is the perpendicular 90-degree angle with the surface. So let's just move this. So one vector, I'm moving just one vector here, one vector F, because you know, if in vector we know that the characteristics you can move the vectors, so I just moved its endpoints there. So what I need is basically this projection upon n. This projection upon n. I cannot just say this time that this is the 3F amount. I cannot say that because it is not perpendicular. It is not collinear with the normal of this surface. So in order to calculate the actual flux, we need to get the projection of F upon all by F with apostrophe F with S. Sorry, I'm not good with that thing. So let's just say that I said the in plural forms. So what I am trying to clear here is that we need all the vector fields projection all the vector fields combined. So we will take each vector and get the projection upon n, and then we can add up those things to get the complete flux that's passing through the entire surface. Okay, so in this case, let's say this angle is theta. Now we can say that this projection will be the f cos theta. So this is f cos theta. Now we can say that f cos theta. So if these three vectors are parallel to each other, then we can see that we will have 3 f cos theta. So the total flux would be 3f cos theta. This is our calculation, but it could have been one vector field. One vector field is like this. It is not parallel with other vector fields. Then surely the theta with respect to the n vector will be different. Let's call it the alpha. So alpha is not obviously equal to theta. So we will have to calculate that separately, right? Then we can add up those things. So this is basically the flux calculation. So finally we can say that we can conclude with this thing that if we want to calculate our fluxes, we need the perpendicular portions or the projection upon the normal of the surface we are calculating, the vector fields projection of the normal on the normal. Okay, good. So what is the surface integration actually is? Okay, so let's say that for this surface, this portion here is ds. This portion is here ds. Why ds? Because ds tends to 0. It is infinitesimally small portion of the entire surface. So if we suppose integrate the ds, we will get s as a whole. We are integrating all the portions of the particular surface. Then we'll get the entire surface eventually if we integrate that. I'm not going with the limits here now because let's abstractly see what we're doing. We know that upon integrating we get the whole portion. Okay, so keep that thing aside. Now the surface integration is written like this. So the surface integration is double integral, and we have a vector field dot n, and here we have ds. Okay, so what does this all mean? We mentioned earlier this is our f field multiplied with our n vector field. Not multiplied, it is the dot product. Okay, so why did you get the dot products? We know for a fact that if we want the projection of a vector upon a vector, we get the dot products. For example, here, if I want the projection of f upon n vector, we will simply, because you have to look for the unit vector. Let's say that this is just an n vector. This is just an n vector. This is just an n vector, and this is not a unit vector. Then simply we cannot just, for example, we cannot just take the projection f dot n. We need to unify this. We need to get the unit vector of the unit vector of the direction that we are trying to get the projected portion of the vector field. So here we obviously have to divide this by its value. Then we will get the unit vector. Now we can multiply this unit vector to get the f cos theta. Now why this thing appeared here? Because the f has its value f and n has its value 1. So 1 times f is equal to f, and that's the cos theta, the angle between them. This is the definition of the dot product of vectors. You can look up on that if you are not familiar with that, but I guess at this point you know already that. So That's the f cos theta. So instead of writing the flux lines, I can here say that 3, this is just a multiplier or the upscaler, I would say. Putting that aside, we could say that this is f dot n. So I think you are starting to see the patterns here. We are getting the f dot n, and we are taking this at suppose let's say this is now our ds. These are the same things, so I will erase that, and this is the ds. At this ds portion, there's only one flux line going, so we are just taking that perpendicular projection of f by the f dot n, and then as this whole portion is only for a ds term, so if you integrate these things, if you integrate this thing with respect to ds, so we will get the whole flux line over the surface. Do you understand now? Like the whole, you can see that there are some, let's say all these are ds. So with each ds there will be a projection, there will be a projection. So if you integrate those things, then we will get the entire vector fields passing through the entire surface, which in terms we can say that this is our flux. So this will be our flux, because we said all the vector fields passing perpendicularly through a surface, or in other words, in line with the normal of a surface, is called a flux. Okay, so if we integrate these things, then we will get flux. And now the question raises, why we are double integrating this thing? Why is there double integration? Why not is there a single integration? Okay, we're double integrating this because to express any surface, we mostly need two parameters. Here, for example, a circle. Okay, so let me draw it clearly. Let's say this is the circle. Now we can parameterize this thing. What is its general equation? X square plus y square is equal to a square. So this is a, and in the coordinate system, if we say that this is our x component and this is our y, so if you parameterize this thing here, we'll get x is equal to a cos theta and y is equal to a sine theta, where a is the radius of this circle and theta is how do I explain this? Okay, so let's say that this is a vector. Let's define this in terms of vectors. So x I cap plus y j cap. Okay, so let's say this is our path. This is our path, x I cap y j cap. So what exactly is the path? This is the round that's moving round and round. This is our path. Okay, so if we say a cos theta I cap plus y, this is a sine theta j cap. So if we consider this our r vector, then this angle with the x-axis is our theta. So as the r moves around and around and around, the theta increases. Thus the limit of the theta will be 0 to 2 pi. Right? This is our 1 pi and this is our 2 pi to complete a circle. Okay, great. And what will be our r? Our r is constant here, so we would say this is a. Great. This is the reason we have two parameters. Yes, I'm admitting that the r is constant here, but it is still a parameter. So when integrating this thing, we have to integrate it in terms of two parameters, in terms of all the available parameters or all the possible parameters. So the amount of parameters we have, we'll have to integrate those times. For example, in surface we are integrating 2 times, and in volume we have like a, b, and h. So we have 3 parameters. This is our height, this is our width, and this is our, let's say, the length. This is the simple assumption or intuition, whatever you say, might be. Okay, so this is how we are doing the 2 times. Now, there's the fun part will begin. We can see that we abstractly said this is our limit s, but in actuality or in reality, we cannot literally define in one word that this is our s. We does not have the complete parameter without our xy axes. You know, in real life, without our xy axis. What is xy axis? Our xy axis is actually the what do I say? It is like the parameter changing things. So let's say in this direction x changes, in this direction y changes, and in this direction z changes. So this gives us a frame in which frame we can literally say that our parameters are changing in this direction, this direction. So we have to somehow convert this s into our x, y, and z. And because this is our surface integration, we will use only 2 coordinate system, like either xy, yz, or xz. Because you know this is a flat thing, flat surface. Surface is always flat that lies in a coordinate plane. So, okay, now here's the fun part comes in. Let's consider our surface is at angle theta. This is our surface, and this is our normal vector. Okay, great. Now let me just draw the axis. Let's this g and actually, you know, yeah, that is c, and x, and in this direction we have our y. Okay, great. You know, this thing is like too much. The bottom line, yeah, move it up. Great. Great. So if we consider this k hat, I'm just going to erase these things for better understanding here. Yeah, great. So k cap. What is k cap? K cap is a unit vector. K cap here is a unit vector in direction of z-axis. Okay. So how do we need that? Let's just say that this is with angle theta. So if I want to calculate the flux actually, okay, so let's just draw our F field, which is our vector field. Let's say this is our F field. This is our F field. Okay, all F fields are on these directions. This is just arbitrarily I'm taking. Okay. Now let's say this is a cylindrical type. You know, actually, I don't actually need a cylinder. I don't actually need a cylinder to calculate. Let's just visualize this thing first. Can you see that this field is actually, okay, let's just color code this, and I'm gonna just this field. Can you see it now? This is our xy plane. This is our xy plane, and this is just like elevating upon the xy plane at a certain degree. The surface, this is our surface S. So if let's say I put a torch here, I put a torch here, and the projection I will see of S, this will be a simply rounder shape. Let's say this is like a rounder shape. This is just a rounder shape, like this. This is a projection. Now, there's the fun part comes in. If let's say infinitesimally small amount of portion of S, I call it ds, and if we take it very small, we can say that that thing is a square. You know, if I like this is our entire circle and this is a small amount of surface, and we can say that many of square makes this entire circle, so that is a square shape. Okay, so the projection of that ds part will be a square, a parallelogram to be exact, because the projection will distort it to some degree. So let's say a parallelogram, but here for calculations I'm just taking it as square. So let's say that this is our this portion is our del x and this portion is our del y. So the total surface is del x times del y. This is our surface. This is the surface on the xy plane. So the projection of that small portion of surface we took ds. This is the projection of that ds on the xy plane. Great. Now, how do we correlate between this ds and del x del y? Let's say, if we want to take a projection on a plane, in 3D geometry, we learned that we can say that ds will be del x. No, let's. I made a mistake. Well, del x times del y. This surface, the projection, will be ds times the cos theta. Now, what is the cos theta? Do you remember what is the cos theta? Cos theta will be the angle between the two normals. So let's say that if we have this surface and this projection is this surface, then the angle between these two normals, this is normal 1 and this is normal 2. So this angle, this is theta. And as you can see, our del x del y is our in xy plane, then its perpendicular is always in direction with z. That's why we took the k cap. So it suffices to say that the theta is angle between k hat and the n hat. Okay, so we can write hypothetically, because we just earlier said, we just know that the projection is our, how do we say it? Okay. So cos theta. How can we define the cos theta again? Let's say k is a unit vector and n is a unit vector. Their value are 1 and 1. So we know that this will be kn cos theta. So putting in the value of k and n, we get the cos theta. Great. So we can say that this will be ds times the value of the dot products k dot n. Now let's transfer this to on side, and we can say that this is ds will be del x del y divided by k dot n, where n is, let's come from the start again. So n here is the normal vector of our surface. The surface could be at any angle, at any orientation in a 3D space. What we actually want is our flux. What we actually want is our flux times the dot product of flux and the normal. So that's why we are going through all these processes. So we can convert this ds with this portion. Now let's say that this d is very small. We can convert this del with d. So dx dy divided by the magnitude of k dot n. Okay, so as you can see here, we just converted our one parameter into two parameters, one variable parameter into two variable parameters. How this will help in our future steps? Now let's say we can put our value x initial and x final. We can now put our limits. Not exactly that, because x is the independent variable, so let's put this in x and xf, and y is our dependent variable, so y initial and y final, because we now have dy and dx. So we can now partially integrate two parameters. That's why surface integration has the double integral. Okay, that part is clear. Okay, and now one vital question: why didn't we initially just multiply this? Let's just erase these f lines and make it a slightly more, slightly increased angle like this. So let's say if. So the question you might ask is, why did not we just get the f projection, f cos alpha, whatever that is, the f dot n in direction to n, and integrate it? Because we simply cannot integrate when the ds is at certain angle or certain orientation, because we don't have a parameter that can truly recreate that surface. If that is in this red circle, let's say, if I try to integrate this thing here at any point, this point the z changes, and then x changes, and then y changes, and this is a chaotic thing. Now here there are three variables, there are three parameters those are changing, the x, y, and z, as the orientation is slightly reverse like thing. Yeah, so these things we cannot just go ahead and integrate the ds without any parameterization. So it is very much efficient if we can reduce one parameter or one degree of freedom to reduce it in 2 dimension, and then we can easily calculate the surface. That's why we are trying to manipulate our surface to make it in 2 parameter variables, so that we can easily integrate this thing. Now if now let's say we got our surface on the projection of the surface. Now we just need the ifs. We just now need our if. So here, let's say this was our okay, let's just put it x and y, these are the limits, and now our flux integration becomes dot n times the ds now becomes dx dy divided by, this is just a scalar part, so this does not changes the orientations or anything like that in the vector field. So this is the magnitude of k dot n to convert our this surface into xy plane. Great. Now okay, so we are nearing towards the end, and here this is our final step. So we successfully converted our oblique surface, or the how do I say it, the different orientation surface, into a plane, xy plane. So we just need to get the amount of f passing through that ds, because the amount of f that will pass through a ds will eventually pass through this portion del x by del y, because this del x del y portion is actually the projection of ds. This is just at another orientation. This is just we are shifting the orientations for our better calculations and taking the limits to integrate the surface. So this will not change how much of flux lines are passing through the infinitesimally small portion ds. So the amount of f line passes through ds will be passing through del x del y. So how much is passing through del x ds? How much f lines are passing through ds? So we can say that ds, it will pass f dot n. F dot n. This is the n component, because I can take the ds, this portion, and you see that n is the normal to this ds. Then the f dot n, this f dot n portion will pass through this ds. So this portion will pass through this del x del y. So this will be f dot n. So if now let's say if we take all the f dot n's, we take all the f dot n's at all points on this surface here, we will get this. Let me take another color. We will get this amount of flux. Are we clear now? I think you can now see what we are actually doing. This purple color, or this violet color, exactly this violet color is actually these blue color lines. The amount of purple color lines here is equal to the amount of blue color lines here. So we just shifted the orientation of our surface entirely and parameterized it in x and y terms to better integrate it, taking the upper limits and lower limits. And that's how we calculate the flux. So our final equation is f dot nds is equal to x initial, x final, y initial, and y final, f dot n del x del y divided by the magnitude of. Now this k is not always constant. You have to find that out based on the question you are given. It is simply the unit vector or the unit normal vector to the converted surface we're taking. So our converted surface is this thing on the xy plane, and k is a unit vector in direction to the normal of this converted surface. So that will be that k. We could have taken another plane, suppose for xz plane, and then we would have here z cap. We would have here z cap dot n cap. I think you are clear now. So this is how we actually calculate the flux lines. How much flux lines are passing through a surface at a certain time. And so vector, the surface integration of vector fields is actually the flux calculation. So I think you are clear, and this is just my first video on YouTube, I think, a tutorial type. I'm just making this for casual purposes. So bye.